Bismillahirrahmanirrahim. Welcome to Diode and Application Season 2, brought to you by, of course, Easy Learn. Let's talk about the topics we are going to discuss today. We are going to discuss about the troubleshooting of the diode, Zener diode that we had discussed. So what we will discuss today, we will try to discuss and check that either Zener diode is working properly or there is a fault in the Zener diode. So what we have to do, basically we are trying to differentiate between a short circuit Zener diode, because there is basically generally two types of the major faults. If the Zener diode is not working properly, either it may be a short circuit fault or it may be an open circuit fault. Okay, so we will try to calculate, or there is another type of fault, and we will try to cover it in today's lecture. Okay, first of all, let's talk about this is from this side, from the start. This is the 120 volt 60 hertz power coming AC power, and this is the transformer, and this is secondary winding of the transformer. From here we are getting our a step down transformer, let's say. So here we are getting, let's say, 25 volts, and this is the diodes, 4 diodes connected to make the bridge rectifier, full wave bridge rectification here, as we discussed in the season 1. And these are the 4 diodes. Of course 1.4 volts will drop here. Let's talk about the practical case. And this is the negative terminal, that is called ground, and ground means all the terminals are connected here. All the grounds means they have a common point. Sorry, this is not a common point. This is the common point here. So this is the positive terminal, and these are the filters, different types of filters available. For example, here is a polarized capacitor used for filtration purpose to remove all the ripples that are here after the regulation. Now it comes towards the regulation at the end. Here we had received a perfect 24 volts, but most of the cases, as we had designed just a single power supply, but we need different types of as depends upon different types of application. We want to operate different appliances, different types of circuit connected. For example, if we have a 24 volt power supply here in this case, and we want to connect a circuit that operate on a 12 volt, then we are not going to design once again different power supply, but we will try to discuss. We will trying to use this same circuit for the 12 volt applications, just maintaining the different regulations, different types of regulators available, because this is a cheap way and efficiency is improved. If we're trying to maintain and create a new circuit and purchase a new transformer and design a new circuit, then of course this is not a cost effective and time saving. So this is not a good thing. So of course all the power supply contains, most of the latest power supply contains a different switch, and we can move this switch to the next, and of course our voltage is shown different changing voltage. For example, 12 volt, 15 volt, 19 or 20 volts, let's say. So these are the different different voltage we can obtain from the different power supplies. So here in this case we want, for example, 15 volt. So we uses 1N4744A. This is the 15 volt Zener diode. As you can see that the positive terminal is connected with the negative side, and the negative cathode is connected with the positive terminal or positive of the V bias. This means it is a normal connected in the reverse bias. This is the normal operating zone of the normal operating region of the Zener diode. So if we will use this limiting resistance, because we should have to be in the limits of the current should be limited in the zone of the in which it can maintain a regulation, because I explained in the lectures when we discussed the Zener diode that we should remain in the zone of the from IZK to IZ maximum. So so we take this resistance value 180 ohm after calculation. And for calculation, if you don't know about the calculation, go to the previous video once again, because we are not going to discuss once again about the calculations here, but we will discuss very precisely. Okay, here 15.5 volts, definitely some voltage are shown exceeding 0.5 volts are exceeding than 15 volts, because these are rated some a little bit higher, because when load is connected, the current will definitely be divided into load and into the Zener diode. So when the current will be divided into here towards the Zener diode, and some part of the current will go in from the load, then automatically this will be decreased. So when load is connected, here for understanding we use a potentiometer that is a variable resistance load, so that we can calculate and check that about our Zener, our diode can maintain a regulated voltage for different values of the resistance. Then after using this calculation that we had discussed in the previous episodes, that I total current, how we can calculate, of course this I can be calculated by using the Ohm's law, V over R, and here V is two voltages are available, that is a 24 volt here in this case, that is coming out as input, or you can see that the main voltage from the output of the after the filtration, and 14.8 volt, that is the V output. So 24 volts minus 14.8 volts divided by that is the resistance that we uses the for the regulation purpose. So total current here is the 15.1 milliampere. How we can calculate the current of the load through the load? So this is the total current that is coming from the this side, and after at this point here the total current after passing through the resistance is 51.1 milliampere. But what is the current? Some part of this current will go to from this Zener diode, while some part of the current will go into the will pass through this load. So I total is equals to I Zener plus I load. So I load can be calculated. If we want to calculate the I load, definitely I Zener will go to the other side and it will be subtracted from the IT minus IZ. We had discussed all the things in the previous episode. So 51.1 milliampere minus 0.25, that is understood, we available on our data sheet as well, is equals to the 50.9 milliampere. So this is the way we can calculate the IL. And so the resistance of the load, minimum resistance means to say maximum load we can connect it, is the 14.8 volts. R is equals to V over I. So 14.8 volt, that is the regulated output voltage we are obtaining here, and 50.9 milliampere. This is the current you can maximum load current that is allowed, because if the further current will pass through this, then it will lose its regulation. We can even not go into the 290 ohm, because this is the maximum the minimum resistance we already connected. And at a peak, you can say we are at a peak, we are almost our Zener is almost at this knee of the curve, that is the IZK. So if we further change, the current will go through the Zener, the current will move, more current will drawn by the load. So if the current will further reduce, definitely it will lose its regulation, because the Zener diode current reduces, and after the reduce, the effect is it goes to this point. As you can see that here in this region, the voltage is changing very rapidly for a very little value of the current. So that's why this is the worst case, and we often show that this is the region at almost 20% tolerated region. You have to be careful when you are when the operating region, because risks are not to be taken, because if your circuit is sometime it may serious damage upon the circuits. For example, mobile phone is, if let's say mobile is connected for the charging, then we cannot take risk, because sometime it may damage the components connected on a board and etc. Zener diode open, for example, this is the first case in which the Zener diode will act as an open circuit. This is the 24 volts coming from out of the power supply, transformer, rectifier, filter, etc. And here, after the regulation purpose, this is the open circuit. And after this, let's say there is nothing connected. This behaves like an open circuit. There is nothing connected, and in this case, if there is, all the current will drop due to the 180 ohm, that is the limiting series resistance, and the voltage will be same, because here 24 volts is coming to this side, and digital multimeter shows the same voltage. Be careful. Sometime like in the previous example, we discussed same situation, 291 maximum load resistance is connected. Let's say it is in open condition. When it is in open condition, but according to the situation, this is again showing 14.8 volt, but here remember this diode is faulty right now, in a fault, because it behaves like an open circuit. There is no, for example, we did not connect it, the Zener diode, it behaves like this. So all the current will be dropped due to this limiting resistance 180 ohm, and due to the 291 ohm resistance, so the voltage is decreased. This is the natural phenomena. For example, if 24 voltage we want to connect a motor here, then definitely, of course, due to the connection of the motor load, volt will drops. So this is because of the load, because maximum load is connected, and already it is operating at worst position, that is IZK. So that's why it does not create a huge problem and a huge change in the voltage. But remember, in this type of situation, we cannot identify the fault. So to identify a fault like this is a very critical fault. If you want to identify this type of fault, this can be only identified in this open circuit at no open circuit fault at no load operating condition, as in the previous slide. This, if you disconnect the load, it will show like this, 24.0 volts. So replace this Zener diode. In this case, this is an incorrect Zener voltage. Sometime when you connect the Zener diode here in this type of case, then we want to check and it shows that 20.0 volts, but if it is a Zener diode of 15 volts, then it may shows 15 or 15.1. It means there is a little bit higher voltage. It means the resistance of the Zener diode should be, internal resistance means impedance of the Zener diode should be higher. Then it should then it's like if it's a 15 ohm resistance inside, internal resistance 15 ohm, it may be a 20 ohm. So it means to say our value of the Zener diode, let's say is showing here, it should we should have to select a higher impedance resist diode. So this is basically the graph should be like this for our case. So this is not basically the fault of the Zener diode, this is just the wrong selection. So this is another incorrect zone, and we can identify. Anyway, this is the power supply, and once again other type, short circuit. This is the way, this is, for example, let's say short circuit. Very easily, this is the very easy situation to be identified. If it is behaves like a short circuit, then all the current will flow through this, and it follows like this type of loop, and due to this you can see that all the current will flow through this, and no current is coming out here, and then 0 volts due to the short circuit, and over this now, and now you are able to identify the faults. These file circuits are in the troubleshooting exercises folder on the companion website. Open these and check if there is working properly or not. Then this is the task I give it in the season 1, that is the unregulated 16 volt DC power supply developed in the season 1. I give you at the end of the season 1 of the diode and application a task, and I know you completed this task, but the task of the season 2 is the same. Just upgrade your previous power supply that you made with a fixed output voltage of the 12 volt. So we will discuss, we had already discussed these different types of the Zener diodes, light emitting photo, and so on, and some other different types. These are the summary of the whole season that we had discussed so far. This is the 25th episode according to me. maybe it's another, maybe I think it's a 25th episode, and we are now over everything. So good luck, and we will try to see you in maybe the next season, if it's season 3, or in the next chapter, that is basically about the transistors. So see you next time. Watch, learn, grow.